Welcome back. In this lecture, we will discuss about the concept of moments in probability theory. Particularly, I will discuss two very important moments, mean and variance, as those will be frequently used in our data analysis. So, suppose I am collecting data from a cancer hospital and I have shown some data here. So, I have collected the number of patients, particularly suppose throat cancer patient, who are getting admitted to that hospital per week, the number of patients, right. So, first week we have 1, third week we have 3 people, and sixth week we have 4 people. So, in this way, suppose for 7 consecutive week I have collected some data, number of throat cancer patient admitted in that week in that hospital. Now, if you have to consolidate the data, what you will do? Your common sense say, okay, I will not report this whole length of table. What I will do? I will report the average number of patient, throat cancer patient admitted to that hospital per week. So, what you will do? You will calculate what we call the mean, right? We will calculate the average. So, calculating average is very easy. What you will do? You will sum all those terms and divide by number of sample, that is 7, and you will get the average value. Average number or mean number of patient who are getting admitted to the hospital, right. Now, I want to do the same mean, same average calculation, but in a bit different way. Let us see that. So, I have written the summation of all the numbers 1, 2, 3, something like that, divided by 7. That is what you will do if you have to calculate the average. Now, let us count how many 1s are there. So, I have 1 here, second one here, and the third one here. So, I have 3 1s, okay. I have 2 4s, right, this one, and 2 and 3 is coming only 1s. So, I can rewrite this one something like this. I have 1, it has come 3 times, plus 2 has come 1 time, plus 3 has come 1 time, plus 4 has come 2 times, and I divide this whole thing by 7. Now, if I take 3 by 7, right, or 1 by 7, what are those? I can write it something like this: 1 into 3 by 7 plus 2 into 1 by 7 plus 3 into 1 by 7 plus 4 into 2 by 7. I can write that. So, that is what I have done here. Now, notice what are these? What is 3 by 7? This is frequency, right? Frequency. How many times 1 has appeared in my data, and what is the value? This is the number value, right? So, each of these term is value multiplied by frequency, value multiplied by corresponding frequency. So, I can generalize this using mathematical symbol. What I can say, what I am doing is I am multiplying the value, a particular value. The value here is varying from 1 to 4, 1, 2, 3, 4, and its corresponding frequency. And if I sum them together, this symbol is for summation. If I sum them all together, what do I get? I get the average or mean, the humble mean that we have learned in school. So, now let us make it generalize. Suppose I have a random number x, which is discrete random number or random variable, which varies from a to b, and I know the PMF, probability mass function. I know it is given here, Px equal to k. So, this is a function, probability mass function, which gives me the probability of a particular value of x. So, then the expected value or mean, remember this is a technical way of saying mean, it is called expected value, right. So, the expected value or mean of x is Ex. This is the symbol we write, because it is expected value, we write E and in bracket the random variable. So, E of x, expected value or mean of x, is equal to summation of a particular value of x into the probability, right. Where I am getting the probability from? I am getting the probability from the probability mass function. And if you remember, in the example of patient data, I had frequency there, and usually if I have a large data set, we consider that for a large sample size, frequency is equivalent to probability. So, we have just mapped that, we have replaced frequency by probability. So, what I have got? I have got summation of values of x into their corresponding probability, and that is my mean or expected value of a random variable, which is a discrete random variable. Now, I want to use the same technique, but I want to calculate the expected value or mean of not x, x is square, right, square of x. So, what you will do? Simple, you will again use the school level idea of mean, as simple as that. So, you will take 1 square, 2 square, 3 square, 1 square, 4 square, like that, and you will sum them and divide by 7 because 7 is your sample. I can again do the rearrangement here. I had 1 square appeared 3 times, see, here and here. So, I have 3 by 7, that is the frequency. How many times 2 square has appeared? Only once. So, I have frequency 1 by 7. Similarly, 3 square has appeared only once, so its frequency is 1 by 7, whereas 4 has appeared twice, so 4 square has appeared twice, so its frequency is 2 by 7. So, I have just multiplied the value again, just like the way we did for mean and the earlier case, and its frequency. I am multiplying them and then summing up. So, using the mathematical symbol, I can write it is summation of the value into its frequency and then sum them together, right. So, then again, just like the mean, I can do generalization. X is my discrete random variable which varies from A to B, and I know the PMA, probability mass function, I know. Then the expected value or mean of x square, in this case remember we are dealing with x square, not x, of x square will be E of x, x square, expected value of x square will be equal to a value square into the probability. This is the probability and this is square of that particular value. So, I have generalized it. So, I have generalized it for a discrete random variable for mean of x or expected value of x, mean of x square or expected value of x square. Why do not I go further up? I mean, why do not I go to x cube, x to the power 4 and something like x to the power m, right, generalizing it broadly. So, what will I get? So, again x is a discrete random variable varying from A to B, and I know the PMF, suppose I know it, then I can write that the expected value of x to the power m, we had done with x to the power 1, that is x, we have done with x square. Now, I am saying expected value of x to the power m will be equal to, using the same logic, a value of that particular variable x to the power m into the probability. Remember, the probability remains same, only the term before probability is raised to m, right, and then you sum them all together from A to B, k will vary from A to B. So, this is the expected value of x to the power m. It is most often written as mu subscript m. So, this is the generalized definition of moment in probability theory. You may have heard that in many lectures or in textbook or some literature, you have heard people are talking of first moment, third moment, something like that. This is the moment, mth moment will be E of x to the power m, and this will be the formula. So, in the first moment m is equal to 1, in second moment m equal to 2. So, if you have paid attention to our concept of discrete random variable and continuous random variable, you must have noticed what we are dealing till now is all discrete random variable. That is why we have PMF, probability mass function, and you may be wondering, what should I do if I have a continuous random variable, x is a continuous random variable, I should have the definition of moment for that also. Yes, nothing will change much, it is very simple. What it will happen, I will replace this P, probability mass function, by the PDF, right, and probability density function, and this summation will be replaced by integration sign. So, it will be integration from A to B, right. So, that is what you will do, that is what I have shown here. We will not go much in detail of this, because going into detail of this summation integration is not required for this course. Just we have to understand what is the concept of moment and how it emerges. It comes out simply from the idea of average or mean that we all have learned in school math, right. So, I have the same data. What I have done, I have plotted that on a number line here, right, and each circle, each of these circle represent each of those result count, right. So, 1 has appeared 3 times, whereas 4 has 2 times, and this pink one is my mean mu or expected value of x. Now, when you consolidate a data, a large table like this, it may have 700 data points or something like that. So, you not only report the mean, but at the same time you also want to know the dispersion of the data. Just telling me that the average number of patient getting admitted, throat cancer patient admitted in the hospital per week is 2.2857 does not really give me the clear picture, because I also want to know how much is the variation from week to week, right. And this dispersion issue, how far it can go, right, how low it can be, how big it can be, this idea, these variations, remember, is always with respect to the mean behavior, right. I want to know how much it will vary from this mean, how much it will vary from this particular mean value. Now, if you suppose want to compare the dispersion or variation of two different data sets, I have one for suppose throat cancer, this one, and I have another data set for breast cancer patient. Now, obviously, the means will be different possibly, and their dispersion will be also different. Now, if I have to compare the variation of these two different data sets around their mean, now if their means are different, then it becomes a bit complicated. That does not make much sense, isn't it, because their means are different. What I want, that I have to do something so that the data set mean become same. The simplest way to do that is that universally when I will get this data, I will do something, some mathematical transformation I will do, so that the mean will become 0. I will do that for every data set, right. So, that is what called centering of data, and it is used for many purposes. I am just showing for one example here for one particular reason, because I want to know the dispersion of the data around the mean. So, I am doing centering. What I am doing? What I have done here is I have taken the value and subtracted the mean of that, right, because this is my mean. So, if you remember, just in the previous slide I have shown the mean is 2.2857. So, I am subtracting that value from each of these values, right. So, I have centered the data. Why I have centered the data? I have now subtracted the value of mean from each of them, and then what happens? Actually, if you calculate the mean of these values, if you calculate the mean of all these centered data, you will find the mean will be 0. You can try that. Just a caution here, the mean is actually not 2.2857. There are some other digits after that. What I have done, just to accommodate in this table, in this space, I have truncated them. So, if you try that in an Excel sheet or somewhere or in a calculator, you will find that if I use 2.2857 as the mean value, you will not actually get a 0 as mean, but it will be a very small number, right. So, you have to accept that is equivalent to 0, otherwise you can take all the digit and actually the mean should come to 0. So, what I have done? I have centered the data. Try to understand why I am saying centered. Look at this data now. Now, the mean is 0, this is my mean now, right, and all the data is dispersed around this 0. You may have a breast cancer data set, you may have a liver cancer data set, you may have a glioma data set. All cases you can do this type of centering with respect to their respective means, and then mean of all these data set will become 0. Now, you can ask, okay, tell me what is the dispersion around the mean, right. So, the issue of variation in mean is gone. Now, I am safe, I can talk of variation. So, what we will do now? We will calculate the moments. We learned the idea of moment, right. So, we will calculate the moments on this centered data, not on x. We will do the moments, apply the concept of moments on x minus e of x. So, how it will look? The same thing, everything will remain same. In the earlier case, I was writing e of x to the power m, right. Now, x is, I do not have x, I have x minus e of x, because that is the centered data. So, I take e of expectation of x minus ex to the power m, because it is the mth moment, that will be equal to, earlier I had k here, right. In the earlier when I was talking of moment, I had k here. So, now in this case I have k minus ex, the mean, because it is centered data, in to the power m, because it is the mth moment, into the probability coming from the PMF. So, this is called central moment, because you are working on centered data. Now, one central moment is very important for our data analysis course, that is called the variance. Variance by definition is the second central moment. You must have learned variance earlier in some other course. So, variance of x, a random variable, is the second central moment. See here, m is equal to 2 of what? It is the moment we are taking for the center data, x minus e of x. That is why it is the central moment, it is second central moment. And you can use the formula of moment, the definition of moment, it will be this one, as simple as that, power will be 2, and you can do some sort of simple algebra to it can be shown is that this one is the variance of x is equal to expectation of x square. You are squaring the data and calculating the expectation. We did it, right? Few slides back we did that, minus square of the expectation of that x. This you can prove algebraically, although you do not need to prove that for this course, but we have to remember these two has different uses. For example, for data analysis work, for large data analysis work, we use this formulation, variance is equal to expectation of x square minus square of expectation of x. This formulation becomes much easier. You can write if you are writing a code to do data analysis, this formulation becomes much easier to do. Whereas, if you are doing some probability based generalized work, this one is more useful. Okay. So, we have reached variance, which you must have encountered earlier, and what we are measuring here, that we have to understand what is the physical meaning. Okay, we have got the it is a second central moment, but what actually it is measuring, what is the physical meaning of variance? Let us look into that. So, the variance is actually a measure of dispersion of a random number around its mean, right? Why I am saying that? Because see what we have here, this is what, x minus e of x. So, that is mean of x is subtracted from x, right. So, this is deviation, this is nothing but deviation from mean, mean, right. So, x minus ex is deviation of a number from its mean, of a value from its mean. Now, that deviation can be positive, that can be negative. Just in the previous example you have seen when I am centering the data, mean is becoming 0, which was earlier a positive one, it is becoming a negative value. So, sometime it will be negative, sometime it will be positive. So, now if I now try to calculate the mean of that deviation, then as some are negative, some are positive, my mean will be 0, that will not make any sense. So, what I am doing, I am taking the square of it. So, I am taking the square of deviation from the mean. So, once you square, negative and positive all will be positive, and then you are taking the average of that square deviation. So, what it is? Variance in a way is nothing but average of square deviation in a way, right, because expectation is averaging, right. So, you are taking the mean of squared deviation. So, for some data point the deviation is very large, some data point the deviation is very low, I am talking of deviation from mean, and you are averaging those deviations square. So, you are getting variance, and as it is average or expected value of a square thing, remember square things are always positive, variance has to be positive always, right. Now, usually we do not report variance, right. When you do data analysis, we do not usually report variance. What you report is usually standard deviation, and that is very easy to understand. Standard deviation is nothing but the square root of the variance. Now, here one point we have to remember. See, if I take the square root of 4, you get 2 answers, right, plus 2 minus 2. Now, which one I should take here? Should I take the negative value also for square root of variance? No. By convention, we only take the positive value, right. So, standard deviation can also not be negative, it will be positive by convention, because it is a measure of distance, it is a measure of distance from the mean, right. So, that measure is an absolute term, so it is always positive, and it is the square positive value of the square root of the variance. That is what we do. So, suppose I am measuring x, x is a random variable. For example, suppose x is the absorbance of a, suppose you are doing a colorimetric measurement of some molecule like protein molecule solution. So, x is the absorbance. Now, from that absorbance you have to get the value of concentration of the protein solution. So, what you do? You have a standard curve, and that from standard curve you get some constant term. You actually use that constant term and multiply the absorbance value to know the concentration of your sample. That is what you do, right. So, what you are doing? You are measuring x, but you are reporting something scalar, something constant multiplied with x. So, suppose I have a random variable which I am measuring x, but from that I am creating another new variable which is nothing but a into x plus b, where a and b both are constants. They are not random variable, right, they are constants. For example, a dilution factor is a constant, right, you are but the sampling that you are doing is random, but the dilution factor will remain constant. Or suppose the example I gave, the protein solutions absorbance, when you convert from absorbance to concentration, you multiply with a constant term. So, if this is the situation, then if I know the expectation of x, what will be the expectation of a x plus b? So, it can be proved, and we do not need to go to the proof, just we have to remember this rule, that E of a x plus b, where a and b are constant, a x is a random variable, it does not matter whether x is a continuous random variable or discrete one, in generalized is a random variable, then this can be written as a into ex, E of x plus b. Now, what will be the variance in this case? Variance is very interesting. Variance of a x plus b will be equal to a square plus variance of x. Remember, b does not appear there because b is a constant, and there cannot be any variance of a constant term, right, it is not varying. So, that is why there is must be a 0 which I have not written. So, it will be a square into variance of x. Now, this is for something I am multiplying and adding with a random number x, but suppose I have two random numbers, or suppose in other way I have two measured random variable, two parameter I am measuring in the experiment, and when we report the data we actually multiply these two, right, and imagine that these two random variables that we are measuring are independent of each other. That means the probability of one does not affect the probability of the other one. So, in that case what will happen? So, for here x and y are the independent random variable, again it does not matter whether it is discrete or continuous, then the expectation of their product E of x y will be equal to E of x into E of y. E of x is the mean of x, E of y is the mean of y. What will happen for the variance? Okay. Variance of x y will be equal to expectation of x square, the mean of x square, into expectation of y square minus the square of Ex and square of Ey. So, now let us move to something else which is connected to the same concept of moment. If you remember, I said I want to understand the mean and variance in terms of moments, because one, it helps us to combine different data and calculate the mean and variance for them using those rules that I discussed just now. And the other reason is that if I know the PMF or the PDF, or in other words I know I am doing some generalized calculation, I know the probability distribution of the variable, right, and then I want to know what will be the mean and variance of that, right. In many statistical analysis and data analysis, the model that you build, you already imagine that okay, there is a hidden Poisson distribution or hidden normal distribution. So, what will be their mean and variance of those distributions? Those can be calculated theoretically simply by algebraically for each of the given PDF or PMF, and I have listed some of those which are very common usually in biological data analysis. Obviously, the binomial will come first. So, in binomial, remember what we are doing, we have n number of trial and p, small p, is the probability of success, probability of having mutation, probability of death, probability of getting 1, probability of getting head, something like that. So, then the mean you can prove, but you do not need to prove for this course, is will be n into p, and the variance you can show will be n into p into 1 minus p, right. Another important discrete random variable that we have discussed was Poisson distribution, right. And Poisson distribution has something very funny. So, in Poisson distribution, remember we had talking about some event which is happening independently with a constant rate, right, and we are trying to find out the number of events happening in a particular interval of time and space. And in this case, the PMF has one parameter mu, the mean, right. So, it can be shown that for a Poisson distribution, the mean and the variance are both same, that is mu, the mean. Now, come to one of the most commonest continuous distribution that we will encounter in any data analysis is normal distribution. And if you remember, normal distributions PDF is defined by one, this is the standard deviation, and mu is the mean. So, in any way your PDF is itself is defined by these two parameters, standard deviation and mean. So, your mean and variance will be mu and sigma square, the standard deviation square. Now, take another one, another continuous distribution, exponential, and if you remember, exponential distribution has parameter lambda. So, it can be shown that the mean of this exponential distribution will be 1 by lambda and the variance will be 1 by lambda square. So, that is all for this lecture. Let me jot down what we have learned in this. The first thing we have learned the idea of moment, and we are trying to learn it because this has utility in different derivations and calculations where probability theory is used. So, the mth moment of a random variable x, where the formula that I have shown it for discrete random variable, but you can have equivalent one for a continuous one, will be is equal to the summation of k to the power m into probability of k. K is a particular value or realization of that random variable. Now, two moments are very important for our work. One is mean, the humble mean that we learned very early in our school, or the average we call, is nothing but the first moment of a random variable or a measurements that you are making, and the variance is the second central moment. It is central because I have centered the data with respect to what? With respect to the mean. So, x minus Ex, that is Ex is the mean. So, and then we have taken the square of that, and then we are taking the mean of that square, right, and we can actually calculate it easily using this relationship E of x square minus E of x's, that whole square. So, this is the variance, and then we have learned certain rules, right, which can be derived from the definition of moments, that if I have a random variable x and if I take Ax plus b, then its expectation of this new variable will be a into expectation of x plus b, and the variance will be a square into variance of x. Similarly, if x and y are independent, two random variable independent, then expectation of xy will be expectation of x into expectation of y, whereas the variance of xy will be expectation of x square into expectation of y square minus the square of expectation of x or mean of x into mean of square of mean of y. So, these are the generalized thing we have learned. I have not discussed how to calculate mean and variance in this particular lecture. We will have a separate lecture where we will discuss about not only about how to calculate variance from a data, but also we will discuss about covariance. We will all see you there in that lecture, but before I leave, let me leave you with a problem to solve. Suppose I have a cell suspension, the first tube I have shown. This is suppose my stock cell suspension, right, and then I have done its serial dilution, that is what I have shown, x square 10 times serial dilution twice, and then from the serial diluted thing I have sampled the cell suspension, suppose 9-10 different tubes. And what we have measured, the data that is given to you is that the final volume is 100 microliter. That means, in each of these I have 100 microliter of cell suspension, and the average cell density in those final thing, although it is not written here, average, this is the final in the final tubes, right, those last left hand side tube. So, the final average cell density is 1000 cell per ml, and we have also measured the standard deviation. We have multiple 19 tubes. So, we have checked what is the cell density in each of them. From there we have calculated the average or the mean cell density, and also calculated the standard deviation. I have given you the standard deviation, that is 10 per ml, 10 cell per ml. Now, I want you to calculate the variance in cell number. Remember, the data given to you is for cell density, cell per ml. So, I am asking you to calculate the variance in cell numbers in the final tubes, mean these tubes. So, you have to calculate the variance from this given data, variance in cell number, nothing else, right. So, if you have followed this lecture, you should be very easy to solve this one. So, try this one and join us for the next lecture. Till then, happy learning.